Okay, so from here it's the second half of chapter 10. So I will consider a new example. So this example was inspired by an actual lawsuit that happened in 2016. So a woman sues Starbucks over too much ice. So this woman sued that there are too much ice but not enough coffee in Starbucks iced coffee. So anyhow, so inspired by, like, of course, this lawsuit was dismissed. But after this lawsuit, I feel like there are not enough ice in iced coffee from Starbucks since then, maybe due to this lawsuit. Anyhow, so I will utilize this example as a numerical example. So suppose that, so we know that Starbucks Grande iced coffee is supposed to be 16 ounces. Uh, but so suppose that someone sues Starbucks that they it's less than 16 ounces. So there is a problem. It's not. So they are cheating. Starbucks is cheating on the amount of iced coffee. So we want to test it. Suppose that you are, say, federal, like agent or like government agent, office agent, who wants to test it, regulate it. Okay, if they are keeping their label uh, true. So then you set up a hypothesis like this. You assume that the iced coffee or grande iced coffee is 16 ounces versus an alternative that the expected amount is different from 16 ounces. Okay? So we have to think about this. Then from based on this hypothesis, we are going to reject the null hypothesis if the sample average is too small or too large. I mean, when you reject when the sample average is too much different from 16 ounces. And if the null hypothesis is rejected, that means Starbucks is cheating. Like the null hypothesis is innocent, and then alternative is punishment. You have to punish Starbucks if the null hypothesis is rejected. But think about it. Why do you have to punish Starbucks if the sample average is above 16 ounces? That does not make sense, right? So the framework that we considered up to here is actually unrealistic, or it's not applicable to most of our empirical, like our examples. So we will change our model, our framework, so that I don't care if Starbucks gives you more than 16 ounces. That's not a problem at all. As a regulator, a regulation officer, I don't care if Starbucks gives you more than 16 ounces. That's not something to punish. But if the amount is smaller than how much it is advertised, then then you have to punish Starbucks. That's our basic motivation. So we are going to change our hypothesis in this way, right? We will change our alternative to this way, or you may write it this way: like you believe that the expected amount is 16 ounces, and you are going to reject it only when the expected amount is less than 16. Or you can just say that your belief is 16 or greater, like include equality and inequality at the same time in the null hypothesis. Anyhow, here the point is the alternative hypothesis. Up to so far in the previous chapter and earlier in this chapter, I actually did not consider the alternative hypothesis at all. I did not think about it more carefully at all. So from now on, it matters. The alternative hypothesis now matters. So then it follows when you are going to reject, when you are going to punish the subject. That determines this inequality. Okay, that we call one-tailed test, right? It's literally, you know why? It's one-tailed test because we only reject only on one side, only on one tail. So you can think about upper tail test or lower tail test. They depend on when you reject. So upper tail test is when you reject the null hypothesis if the data sample average is too large. So it is supposed to be a certain level or below, but if it's too large, you have to regulate. And our example is actually the opposite. Our example, the grande coffee must be at least 16 ounces. That's a lower tail test because the problem arises when the sample average is too small. You are going to reject and you are going to punish when X bar is too small. So you reject on the lower tail. But yeah, so no matter what, basic idea is the same, like upper side, lower side. It's just depend on the context. And of course, algebra are symmetric, seems parallel. So I will now, for now, following the example, I will focus on the lower tail test. Okay. So yeah, in our example, we have to rewrite our hypothesis, our pair of hypotheses in this way. So this null hypothesis does not need to be changed. Does not need to be changed, but your alternative must be changed because that the alternative hypothesis determines when you reject. That's the main idea. So you have to determine what you reject by the alternative hypothesis. So, okay. So then also graphically, you can write it this way. So I believe that the mean is 16 ounces because I don't think Starbucks will give you more than that, right? There is no reason for them to give you more, right? So I believe they will just follow what they say. But due to the random error, human error or measurement error, sample average will be normally distributed around 16 if they are innocent, if they are following the rule, right? So if their label is correct, the center would be 16, but it will be a little bit suspicious if the observed sample average is too low. So the suspiciousness only goes in one direction, right? So if the actual sample average is greater than 16, I don't mind. That's not a problem. So we don't care about that side anymore. We only suspect when it is too small. That's the only difference. Okay? So then, I don't care about the upper side, right side. I only care about the left side. So I will think about so suppose that you observe X bar here. Then in the previous chapter, we considered the other side tail probability too. But now we don't. We don't care the right side tail. We only care about the left tail. So p-value is only the left tail probability. Right tail probability is not included. In other words, remember, the p-value is the ranking of suspiciousness, right? We count from the most suspicious outcome down to what you observe, right? And in the previous chapter, we have to think about suspicious outcomes from both tails. But in this example, right side outcome is not suspicious. So it's only from the left side. So that's why our p-value must change, right? We only calculate p-value from one side, okay? And if you take the critical value approach, the idea is the same. We are going to reject only on the left side, only when X bar, the sample average, is too small. So rejection region is now only on the left tail. In two-tail test, our rejection region was on both tails because we simply reject when the sample average is too much different from our hypothesis. Either side, right? Too much different means too small or too large. But in our example, we only reject when it is too small. So we have only one side rejection region. That means we have only one cutoff. That is one critical value, right? Only one critical value that must be smaller than your null hypothesis. So your null hypothesis is 16, and you allow up to a certain margin below your hypothesis. But if it's too small, then you have to reject, and Starbucks is doing something cheating, right? Okay, this is the basic idea and basic scenario, and it's a natural extension of two-tailed test, right? So let me then go over the details, like mechanical differences. First, t-statistic does not change because t-statistic does not include any any idea of rejection. So the definition of t-statistic is the standardized difference. It is neutral. It is rejection neutral. I don't care about when you reject, and I don't care about what is suspicious. T-statistic is just difference. Okay. But p-value was defined as the ranking of suspiciousness. So it depends on who you think suspicious, right? So p-value should change, right? So two-tailed test included two-tail probabilities from the lower side, from the upper side. But in one-tail test, you only include one side tail. One side is where you are going to reject, right? So only when you think suspicious, then include that into probability, right? Upper tail test, you are going to reject when the sample average is too large, then the probability is only on the upper side, right? Greater than your t-statistic. But lower tail test, you reject when it is too small, so p-value is the probability on the smaller side. So that's the difference. But either way, t-statistic or p-value, the rule is the basic decision rule is the same. In the end, we are going to reject the null hypothesis if the p-value is smaller than alpha, significance level, right? So I calculate t-statistic like this, and use the t-statistic to calculate the p-value. P-value changes, but the t-statistic and decision-making rule does not change, right? Do not change. So the final rule is the same, okay? But if you use the t-statistic approach, then t-statistic itself does not change, but the decision rule changes, right? So remember, when two-tailed test, like t-statistic is the standardized difference. If the difference is too large, then you are going to reject the null hypothesis. So then too large means if the t-statistic is outside plus minus z alpha over 2, like smaller than minus z or greater than plus z alpha over 2, then you are going to reject. However, now in one-tail test, you are going to reject only on one side, as I said. But what is tricky here is you have to adjust z alpha over 2 to z alpha. Like so here in two-tailed test, the reason why we are using z alpha over 2 is because we use we are going to, so remember, we are willing to reject alpha probability, but we have to reject if it is too small or too large. So the rejection probability alpha must be divided in half. So we are planning to reject alpha over 2 from the top, and we are going to reject the other alpha over 2 from the bottom, right? On the lower tail, there will be alpha over 2 rejections, and from the upper tail, we are going to reject alpha over 2. So in total, it would be alpha in two-tail test. But now, in one-tail test, still we are going to reject alpha probability. But we are rejecting all the alpha probability on one tail. So we have to change our threshold. So if you look at only one side, you have to reject twice more, right? More rejections are coming from one tail than the two-tail tests. So if you are doing upper tail test, if you are rejecting from the top, then you are going to reject top alpha probability. In a lower tail test, you are going to reject alpha probability from the bottom. So you are going to reject anything smaller than bottom alpha probability. Okay? So now alpha is not split on both sides. So that's another key difference in one-tail test. So now if you take the critical value approach, then the first the main difference is we only have one critical value. In two-tail test, we had to have two critical values, upper critical value and lower critical value. But now we only have one because, again, only one rejection region is only on one side, right? So earlier, we have these two inequalities. If it's smaller than lower critical value or larger than the upper critical value, we are going to reject. But now it's either way, greater than something, greater than a critical value, or smaller than a critical value, depending on when you reject. So then, your sole critical value, single critical value, will be either plus or minus. So it should be either greater than your null hypothesis or smaller than your null hypothesis, depending on where you reject. And also, z alpha over 2 becomes z alpha. By the same logic, we are going to reject whole alpha probability only on one side. So you have to put alpha as a whole. But the other structure is the same. Standard error, and the center is, again, the starting point is the hypothesis. So you just allow different margin only on one side. That's the major difference. Okay, so this is a brief introduction to one-tail test. In the following video, I will continue like one more page. Oh, I'm sorry. So I'm not done. So remember, z alpha over 2 is replaced by z alpha. So I'll give you the approximate numbers that you are going to use. So 10%, 5%, 1% implied 1.64, 1.96, 2.58. These numbers applied to confidence interval and two-tail test. In those cases, they are the same in the sense in that they are intervals. They consider both tails, both sides, right? The margins are added on plus minus sides. But now we are looking at only on one tail, so the probability is the constants are, the values are now 1.28, 1.64, 2.33. So the numbers change it. So let me show you how it works in here. Say, so let's start from the significance level. Like it's 1% or 5% or 10%. That means these are basically probability of rejection. Okay? Remember, and then rejection on one side. Rejection on one side is in two-tail test. Let me first show you two-tail test. It's half of these guys. Okay, and then you are going to get, let's think about this, from the bottom, from the lower tail, you are going to get these numbers. And if you round, these are the familiar numbers we see now, right? But what's the difference here is significance level does not change, but we are going to change this rejection on one side. Now it's not divided by 2, right? So if you're willing to reject 1%, then 1% is coming from only one side, so this does not change. And then at that side, the number lower cutoff must be minus 2.33, right? So these are the new values here, right? So this is the main difference between a one-tail test versus two-tail test. Okay, so I will go back to our numerical example in the next video. So when we are going to use those numbers in our numerical example. So just don't be confused. I understand it's very confusing. You don't need to memorize them, but when you need, you can just come back to this slide. But you just need to choose the correct one. You need to understand what you have to choose based on like the alternative hypothesis and the significance level. Okay, so thank you for watching. Yeah, I will go to the numerical example in the next video. Okay, bye.